Welcome everybody to Algebra 1, Section 6.2, Solving Systems of Equations by Substitution. So the substitution method, similar to the graphing method, will get you the point where two lines or linear equations intersect or meet. And it's also where the what value or what ordered pair is true for both equations. And you do the substitution method, or the substitution method is defined as a method of solving systems of equations by substituting one equation into the other. So just like when we did graphing, the graphing method, we graphed lines. Well, similarly, when we do the substitution method, we will be substituting things. And so we have three basic steps that we'll be taking to solve. And the first step is one that we don't necessarily always have to do, but on a lot of problems we will need to do it. So the first step is to solve one equation for x or y. Either one, it doesn't truly matter. We have our preference. Step 2 would be to substitute this expression into the other equation. Note the other equation is important there, and solve for the variable. And then step 3 is going to be to substitute the answer, the value of the variable you found, into our revised equation from step 1, or truly any equation that we have at that point, and solve for the other variable. So step 2 will give you either x or y, depending on what you did in step 1, and step 3 will then give you the other variable that you did not solve for in step 2. Let's go on to number 1 here, where we're going to solve each system by substitution. And so on number 1, we have a system of two equations, y equals 4x minus 1 and y equals 2x minus 5. We're able to know it's a system because of the structure right here, just like we saw in section 1 where we solved it by graphing. And just like when we solved it by graphing, we're going to get an ordered pair, an x comma y, from this solution, and it would be where they would intersect or what would be true for both equations. And we said that step 1 was optional, or not optional, but only occurred sometimes. And when it occurs, when you need it, is when an equation is not solved for x or y, when we don't have at least one equation solved for a variable. And here we have both equations are solved for a variable, so we do not need step 1. Here we have both equations are y equals everything else. So we move on to step 2, where we substitute the expression into the other equation and solve for the variable. So just as if I were to just magically just change this to y equals 2, okay, what I could do is I could take this 2 and I could substitute it in for y. And I could say 2 equals 2x minus 5, and I could start solving this for x by adding 5 and dividing by 2 and getting x equal a number. In the same exact manner, I can say that since y equals 4x minus 1, I can substitute that in for y, just like I was able to substitute 2 in for y if y were to equal 2, even though it's not just a number, but rather an expression. And so I can take 4x minus 1 and replace y with it. And so then I will continue on with the rest of this equation and write my equal sign, and now I'll write 2x minus 5. So I rewrote my bottom equation, but I substituted y with 4x minus 1 because it's equivalent to 4x minus 1. And now I solve this new equation for x. And I have x's on both sides, and so I'm going to go ahead and subtract 2x from each side because I always like to move my smaller of my two variables in order to solve this equation, just like we did back in Unit 2. And I get 2x minus 1 equals negative 5. And so now if I add 1 to both sides, I get 2x equal negative 4. If I divide by 2 on both sides, I get x equal negative 2. Now we're not quite done yet because, as you may recall from our previous section when we solved by graphing in 6.1, that we had ordered pairs for answers in x comma y. Well, we only have the x. We still need the y for the ordered pair. And so how we find that is by doing step 3. For step 3, we substitute the answer we got, which is x equals negative 2, into, it says, the revised equation from step 1, but we didn't have to do step 1, and truly you can do any equation. So we could do substitute x equals negative 2 into either of these original two equations, whichever one you think might be easier to work with for you. And so I'm just going to go ahead and pick the bottom equation here, just because why not, I suppose. And I'll get y equals 2 times negative 2 minus 5. And so now I'm going to go ahead and solve for the, quote, other variable. Well, since I already found x, that makes the other variable y. If I had found y first, which we will have to do on some problems, then my other variable would be x. And so now I'll go ahead and do the order of operations here to get y equals negative 4 minus 5, which results in y equal negative 9. And so now I have my x and my y, and I'll write my answer as an ordered pair. Negative 2 comma negative 9 is my answer. And just like we did when we graphed, I showed that, hey, we can verify our answers by plugging into both equations and showing that it is true for both equations. And so we can do that here, and it would in fact work. And if we had plugged negative 2 back into the top equation, you would get the same exact answer for y to equal negative 9. Now you may be wondering, Mr. Kossel, what if, since y was equal to everything else in both equations, y was already solved for in both equations, what would happen if we were to have taken this 2x minus 5 and substituted it into the top equation instead? Well, let's look what would have happened. So instead of y equals 4x minus 1, we would take 2x minus 5 in place of y and set that equal to 4x minus 1. And this is actually the exact same equation as we see over here in the orange. The only difference is that the sides are flipped around. And this just demonstrates the reflexive property of equality, which says that we can flip equations around and it's still the same equation. So it doesn't matter whether you wrote it as the blue or the orange, it's the same equation regardless. Moving on to number 2 here, we see y equals 6x and 2x plus 3y equals negative 20. So we have one equation where a variable is by itself, and all we need is one equation for a variable to be by itself. And so what we do is we say that y equals 6x, or is the same thing as 6x. And because that is the case, we can take this 6x and substitute it in for y in the other equation. And so instead of 2x plus 3 times y, it's going to be 2x plus 3 times 6x. Because y was multiplying with 3, 6x will do the same exact task. And we don't still write the y, we replace or substitute the y for 6x. And we get this equal negative 20. So I just rewrote this bottom equation, but instead of y, we have 6x because that's what y is equal to. And now we go ahead and solve this for x by doing 2x plus 18x, multiplying 3 times 6x. And I'm going to go and combine like terms and getting 20x equals negative 20, dividing by positive 20, x equals negative 1. And now I take that and I plug it into whichever equation I think might be easier. And the top one seems easier to me because all you'll have to do is multiply by 6 to have your answer, because y is already by itself and I don't have to add or subtract anything. That appeals to me greatly. So I'm choosing the top one, but if you choose the bottom one, you should still get the same answer if your math is correct. So I'll get y equals 6 times negative 1 rather than 6 times x, and that gives me y equals negative 6. And so that's the ordered pair negative 1 comma negative 6, x comma y. On to number 3 here, we have an equation where a variable is solved for. In this case, the top equation has y solved. And so I'm going to take this x plus 9 that y equals, and I'm going to substitute it in for y in the other equation. So instead of 3x plus 8 times y, it's going to be 3x plus 8 times x plus 9 equals negative 5. Now notice in all three, or in the last two problems we've done when we had to multiply something times our what we're substituting, I'm putting it in parentheses. And I'm doing that for this very reason on this problem. So that way we distribute 8 to both of those, because that's all y, because y equals all of that, and 8 is multiplying times whatever y happens to be. And so now I have 3x plus 8x plus 72 equals -5. And I go ahead and combine like terms, and I'll get 11x plus 72 equals -5. And if I subtract by 72 on both sides, so that way my variables are on one side and my numbers are on the other, I get 11x equals -77. And dividing by 11, I get x equal -7. Now that I have this answer, I need to plug it back into either of the original two equations, I don't care which, to find my answer. Now I do have a preference, however. My preference is to plug into the top one personally, because the numbers are smaller and I don't have to multiply x with anything. That appeals greatly to me, as well as it's already solved for y. So I have y equals -7 plus 9 instead of x plus 9. And that results in 2. So I now have the ordered pair, -7, 2, x, y. On number 4 here, we once again have an equation where one variable is solved for. It's the top equation, and x is solved for this time instead of y, and that's perfectly fine. So what we do is we take this 4y plus 7 that equals x, and we substitute it into x this time. Before we substituted it into y because it was y equaled everything else. Well, now it's x equals everything else, so we can replace x with it. And so instead of 2 times x, I get 2 times everything that I just plugged in. 4y plus 7 minus 6y equals 12. And I'm going to distribute my 2, and I get 8y plus 14 minus 6y equals 12. I do want to pause and note that at the step here, this one is green, this one it was the light blue, this one it was the dark blue, and this one up here is the orange. And in all 4 of these steps here, you may notice that we only have one of the 2 variables. Now, by that I mean we only either have x or y. Now we have 2 x's or 2 y's, but we don't have an x and a y. We have x or y. And that's the whole point of substitution, is to get it to where you only have one variable rather than 2 different variables. So that way we're able to actually solve this equation. So now let's go ahead and continue solving this problem. And so I'll do that by combining my like terms. 8y minus 6y is 2y plus 14 equals 12. Then we're going to go ahead and subtract 14 from both sides. And 2y will equal -2. Divide by 2. And y equals -1. So now, since I solved for y first this time, when I plug it back into one of my original equations, I'm going to be trying to find what x is. That's here. That is my other variable this time. And I'm going to pick my top equation personally. Either equation could be picked, but the top equation is going to be easier for me because x is already solved for. And so x equals 4 times -1 plus 7. 4 times -1 is -4. And -4 plus 7 is 3. And that makes my ordered pair 3, -1. Now notice, even though I found -1 first, it still comes second this time. Rather than before on problems 1, 2, and 3, the number I found first came first in the ordered pair. And the reason the reason I put +3 first is because that's what my x value is, because it always goes x, y. Now we're going to start seeing on this next page where we actually have to do step 1, where we are going to have to solve an equation for either x or y. So on number 5 here, we notice that neither variable is solved for in either equation. We do have a 1y equals, but we have 2x plus 1y equals. For a variable to be completely by itself, it has to be the only thing on that side of the equal sign. And so I need to solve for one of these 4 variables. And of these 4 variables, there's going to be an easiest option. The easiest option is typically If any of the four variables here, in this case, purple, green, blue, and orange that I have highlighted here, the x and the y in the top or the bottom equations, if any of them have a coefficient of positive 1, that will be your easiest one to solve for. So in this case, the green variable, the y in the top equation, will be my easiest one to solve for because it has a coefficient of positive 1. Now, we actually don't have any problems today where we'll have another scenario where it won't have a coefficient of positive 1, or rather a coefficient of 1, whether it's positive or negative. And so I'll have to talk about later what would happen if there was a coefficient of a different number. Now, if there was a coefficient of negative 1, however, rather than positive 1, that's your next best scenario, next best pick for a variable. So the best pick is a variable with a coefficient of positive 1. Your next best is a coefficient of negative 1 with a variable. Now, that being said, let's solve for that green variable here, the top y. I'm going to do that by subtracting 2x because it's being added with 2x. And so if I do this, I end up getting y equals negative 2x minus 2. And I'm always going to be putting that negative 2x before the negative 2 because I want it to be in slope-intercept form, because I just want to keep in that habit like we've developed for graphing. Now that I have y by itself, I can take negative 2x minus 2, well, y equals 2, and plug it in. Now, I cannot, repeat, cannot plug it into the same equation we just solved for. And the reason why is it's going to throw off our answer and get us what we call a false IMS, or false implementing solutions. It's going to make it seem as if they're the same line, even though more than likely they are not. And so instead what we have to do is plug it into the other equation. And it does actually clarify that in step 2 as well, the step 1, 2, and 3 for solving these. And so now I'll have 5x plus 3 times negative 2x minus 2 equal negative 8. And so I'm going to go ahead and distribute my 3, and I'm going to get 5x minus 6x minus 6 equals negative 8. Combine like terms, and I'm going to get negative 1x, or negative x, minus 6 equals negative 8. I'll add 6 to both sides, and I'll get negative x equals negative 2. And then I'll go ahead and divide both sides by negative 1, and I get x to equal 2. Now I can take this and plug it into either my original two equations, or, as I mentioned in step 2, the revised equation from step 1. This would be the revised equation from step 1. Now, the reason why somebody might choose this equation over the other two is because it's already solved for y. And that can make your life easier since we're now looking for the variable y. And so if I plug it into that revised equation, that new equation we made, we get y equals negative 2 times 2 instead of negative 2 times x minus 2, because x equaled the 2. So that's why it goes here. And now as we do order of operations, we get negative 4 minus 2, which is negative 6. And so that would be the ordered pair 2 comma negative 6. On to number 6 here. Once again, we have to pick which of these four variables to solve for, either the top x, the top y, the bottom x, or the bottom y. And of those four options, only one has a coefficient of positive 1, so that is going to be our best option. The orange one that I have circled, the y in the bottom of the two equations. Now, you could get the answer by solving for any of the four variables, and it would work as long as your math is correct. However, you'll be making your life harder to do so. So I'm going to go ahead and subtract 2x under the addition of a positive 2x, and I get y equals negative 2x plus 9. And now I'm going to take all of this and plug it into the y in the other equation. Once again, always the other equation. And I'm going to emphasize that this is a y because I kind of covered that up. I'm going to get 2x minus 3 times negative 2x plus 9 equals negative 11. Now, this can be a very tricky part here for a lot of people because of this negative with the 3. As we distribute, you must remember, going back to our very first unit in Algebra 1, that this is really a negative 3 that is multiplying with both negative 2x and positive 9. So it'll give me positive 6x and negative 27. Now I'm going to go ahead and combine like terms to get 8x minus 27 equals negative 11. Add 27 to both sides. And I get 8x equals 16. As I divide both sides by 8, I get x to be 2. Now I can take that and plug it into either my original two equations or my revised equation that's already solved for y. I'll do just that, and I get y equals negative 2 times 2 plus 9. That is y equals negative 4 plus 9, which is y equals 5. So that is the ordered pair 2, 5. On the number 7 here, as we pick a variable to solve for, we look and say, okay, do any of these have a coefficient of positive 1? And sure enough, the blue one and the top x does. And so we're going to solve for that one by subtracting 5y from it, from both sides of the equation, and getting x equals negative 5y plus 4. Now I can take all of this and plug it into the x in my other equation, getting 3 times negative 5y plus 4 plus 15y equals negative 1. Now I will distribute my 3 and getting me negative 15y plus 12 equals 15 plus 15y equals negative 1. As I combine like terms, I end up getting 0y, or no y at all, and I get 12 equals negative 1. Now, we got down to a place where we have no variables, and so we need to ask ourselves, is this equation true or false? Is this statement accurate? Does 12 equal negative 1? Well, of course 12 does not equal negative 1. And so then we say the answer is no solution. That was the case whenever we had this type of scenario as well in Unit 2 when we had equations that we solved for. Now, when this is the case, no solution, that means that the lines never ever intersected, which meant that the lines were parallel. So once again, when you have no variables in your equation and it is false, it is no solution. We'll talk about later what happens if you get the scenario but the equation is true. On number 8, we once again need to solve for a variable. My best pick is whichever one might have a coefficient of positive 1. That's this x up here. So I get that by itself by subtracting 4y from each side. And I just get x equals negative 4y, because this is just 0. So I could write plus 0, but I certainly do not need to. Now I take this negative 4y and I plug it into the x in the other equation. And I get 3 times negative 4y plus 2y equals 20. So as I multiply 3 with negative 4y, I get negative 12y plus 2y equals 20. I combine like terms and I get negative 10y equals 20. And I divide by negative 10. And I get y to equal negative 2. I plug that into any equation, whether it's one of my original two or my revised one. I'll plug it into that new one. I'll get x equals negative 4 times negative 2. And that gives me x equals 8. So that is the ordered pair 8, negative 2. Moving on to number 9 here. The variable that would be best for me to solve for is this bottom y, because it has a coefficient of positive 1. I will do that by getting rid of the 2x. It's currently positive and adding, so I will subtract it to undo a positive 2x. Doing it to both sides gets me y equals negative 2x plus 18. I'm going to take all of that and plug it into the y in my other equation. Now I get 6x plus 3 times everything that was here, negative 2x plus 18 equals 54. I get 6x, I distribute the 3 and get negative 6x plus 54 equals 54. As I combine like terms, I have 0 x's left, so I do not have to write any x's. If I write a 1x, if I write x, that means it's 1x, and that's wrong. and I get no variables, and I look at this equation and say, is this true or false? Does 54 equals 54? Well, sure thing, it does. And because it is a true statement, a true equation with no variables, this is infinitely many solutions, or IMS. This means that the two lines are actually truly one and the same. They just look quite different. On to number 10. So the variable that would be easiest to solve for here would be this top x, because it's a 1x. I will do that by adding 3y to both sides. I'll get x equals 3y minus 2. And now I take all of 3y minus 2 and plug it into my other equation. And I get 10x, which means 10 times, not 10x, but 10 times the new x, which is 3y minus 2, plus 8y equals negative 20. We distribute the 10, and I get 30y minus 20 plus 8y equals negative 20. So I combine like terms, and I get 38y minus 20 equals negative 20. I add 20 to both sides, and I get 38y equals 0. A lot of people, when they see the number 0, panic and say, no solution. And that's just not the case here, because we still have a variable. We treat 0 like we do any other number. So just like if we had any other number over here on this side, we divide by 38. So we divide by 38. And 0 divided by any other number in all of existence is 0. And so y is 0, which is a place on the graph. And so now we go ahead and plug it into any equation. So I'm going to plug it into my newest equation here, the one that I worked on, and I get x equals 3 times 0 minus 2. And boy, do I love multiplying by 0, because anything times 0 is obviously 0. So 3 times 0 is 0, and I get 0 minus 2, which is just, of course, negative 2. So now I have my ordered pair of negative 2 comma 0. Last but not least for this page, number 11. Number 11, there is no variable that has a coefficient of positive 1. So as I mentioned after doing number 5, our next best bet is that any variable that has a coefficient of a negative 1. And that would be this one right here. So now I'm going to go ahead and start solving for that y by subtracting 3x. And I get negative y equals negative 3x minus 8. Y is not quite by itself, so I divide everything by negative 1. And I get y equals 3x plus 8. Now I can take all of this and plug it into, once again, the other equation. It has to be the other equation. If you plug it into the top equation, again, the same one we were working on, you'll get a false IMS, to where you get an equation that's true with no variables. And we get 5x plus 2 times 3x plus 18 equals 5. So I distribute my 2, and I get 5x plus 6x plus 36 equals 5. That should not have been an 18. Pardon me. That should have been a 16, because I did 2 times... Sorry, that should not have been 18 in the parentheses. That should have been an 8 in the parentheses, which would then make 2 times that 8, 16. My apologies on that error. I'd copied that down wrong from the orange to the green. Now as I fix this, I combine like terms and I get 11x plus 16 equals 5. I had to subtract 16 on both sides, and I get 11x equals negative 11. Divide both sides by 11, and I get x to be negative 1. I plug that into any equation, so I'll choose this newest one, take my life a little bit easier, and get y equals 3 times negative 1 plus 8. 3 times negative 1 is negative 3. And if I add 8 to that, we will get 5. Give me the ordered pair negative 1 comma 5. Now, I did mention that I wanted to talk about what would happen if we had no coefficient of positive 1 or negative 1 to start, and so let's talk about that. And so if I were to have one equation that was maybe 4x plus 2y equals 6, and the other equation that was 3x plus, I changed colors there without even realizing it, 3x plus 5y equals 9. So between these four options, there is still a best option or an easiest option available to you. And what that would be is whichever variable has a coefficient that divides into all other numbers in the equation. I'll say that again. Whichever variable has a coefficient that divides into every number in the equation. So for example, here in this top equation, it would be this 2y, because 2 divides into 4, 2, and 6, and will create no fractions. Now the reason I say that is because if we were to solve for this y, we'd have to subtract the 4x, getting us 2y equals negative 4x plus 6. And then our next step would be dividing by 2, which is the whole reason why I said we'd want to make sure that this division would go well, and so that's what we wanted to focus on. If I had solved for this x, I'd be dividing every number here by 4 eventually. Just this would be a negative 2 before I do it, but I'm dividing every number here by 4, which I can do. I'll just get a fraction. If I solved for this x, I'd be dividing every number by 3 eventually. If I solve for this y, I'd be dividing every number by 5 eventually. And so while we're capable of doing all of those things and having these fractions and using them, it makes our life quite a bit more complicated, where we can just instead say, oh, let's make our life a little bit simpler and create a scenario where we don't have to deal with extra fractions. And you do that once again by selecting the variable that has a coefficient that divides into everything. On to this next page, we're going to compare graphing to substitution. And so we're going to be solving these equations by both graphing and substitution, and just showcasing that you get the same answer either way. Now, number 1 here, you get y equals x plus 6 and y equals negative 2x minus 3. You'll notice that's for both of these. And so on the graph, this first equation, which I'll do in light blue, the slope is 1 or 1 over 1, and the b is 6. And so I'll begin at b, noticing that this graph is another 10 by 10. So 10 up, 10 down every direction. Now I have my answer key handy, so I'm able to say, oh, I know that I need my points to go down and to the left here, rather than maybe a different direction. And it doesn't want to let me get my line exactly on where I want it, so I'm just going to have to do it manually, unfortunately, but that's okay. And then my other equation, my slope is negative 2 over 1, and my b is negative 3, my y-intercept. And they intersect right there at negative 3, 3. And so that'd be my answer, negative 3, 3. And so we're going to see as we solve this one by substitution, we'll get the exact same answer. So here we have both equations have a variable solved for, so we just pick one of these to plug into the other equation. Instead of y equals everything else, it's x plus 6 equals everything else. And that equals negative 2x minus 3. I'm going to go and add 2x to my two variables. And I get 3x plus 6 equals negative 3. Subtracting 6 gets me 3x equals negative 9. Dividing by 3, and I get x equals negative 3, which we notice is what the x value is here. Now, as I plug it into either original equation to solve for y, I will plug in the top one here, and I get y equals negative 3 plus 6 instead of x plus 6, which is just 3. And so that would be my ordered pair, negative 3, comma 3, which once again is the exact same answer we had when we graphed it. And that'll happen every time as long as you do both methods correctly, of course. Number 2, since we spent all of 6.1 working on trying to get these into slope-intercept form, y equals mx plus b, I'm not going to show the work here on getting them into slope-intercept form. Rather, I'm just going to show the result. So this, when you get it in a slope-intercept form, ends up being y equals 5x plus 5, whereas our other one ends up being y equals 1/2 x minus 4. So as I graph this top equation, the slope is 5 or 5 over 1, and the b is 5. And my graph would look something like this. And my other equation has a slope of 1/2 and a y-intercept of negative 4. And we can see where the intersect is right here, which is the ordered pair negative 2 comma negative 5. Now, as we solve this by substitution, which once again I showcased 10 examples on the previous 2 pages of how to do that. So I'm going to jump to the variable being solved for in this top equation as I solve for this top y with a coefficient of negative 1 to begin with. And just like we solved for y in the other, solving by graphing, it results again in y equals 5x plus 5. Thankfully that didn't change. It'd be awkward if it did. And I plug this into my other equation, and I get 3x minus 6 times 5x plus 5 equals 24. And so now as I distribute the negative 6, making sure I do note that this is a negative 6, I get 3x minus 30x minus 30 equals 24. Now I combine like terms and I get negative 27x minus 30 equals 24. I add 30 to both sides, and I get negative 27x equals 54. I divide by negative 27, and x equals negative 2. Plug this into my newest equation. Any equation would work. And I get y equals 5 times negative 2 plus 5, which is really just y equals negative 10 plus 5, resulting in y equals negative 5, which is the exact same answer we got previously when we solved by graphing of negative 2 comma negative 5. Example 3, this top equation ends up becoming y equals 2/3 x plus 4. The bottom equation ends up equaling y equals negative x plus 9. Top equation has a slope of 2/3, y-intercept of 4. As I begin to graph that, we end up getting these points. And I graph my other one, slope of negative 1 over 1, a y-intercept of b of 9. And we can note that they intersect right there at 3 comma 6. Well, I already know what the either equation solves for, but I'm just going to go ahead and solve this bottom one here. For either x or y, it doesn't matter which because they both have a coefficient of positive 1, so I just pick one. Let's say I solve for x, because I suppose why not, by subtracting the y. And so I get x equals negative y plus 9. I also could have solved this top equation, however, I'd be getting fractions, which I could do, but I'd rather avoid it if I can. I plug all of this into x in my other equation, and I get 2 times, instead of x, but 2 times negative y plus 9 minus 3y equals negative 12. distributing the 2, and you get negative 2y plus 18 minus 3y equals negative 12. That is negative 5y plus 18 equals negative 12. So if I subtract 18, I get negative 5y equals negative 30. Dividing by negative 5. I get y to equal 6 like we did previously. And I plug this into any equation. I'll choose my newest one that I modified and get x equals negative of 6 plus 9. And negative 6 plus 9 is 3. So the ordered pair is 3, 6, just like we got when we graphed it. On to number 4. This first equation ends up becoming y equals 1/3 x plus 5. The bottom equation is actually already in slope-intercept form, kind of, because there is a slope that is undefined and no y-intercept. There is no solving it. It's done with the second equation. So the slope on this first equation is 1/3, where the b is 5. And I graph the other equation. It's x equals a number, which means it's a vertical line at x equals negative 3. So when x is negative 3 everywhere. And the intersection is right here in the green, which is negative 3, 4. Note, x was negative 3 and x is negative 3. That'll always be the case when you have an equation that's x equals a number or y equals a number, that the x or y value will be that number. So speaking of, since we know x is just going to be negative 3, we actually just take this and plug it in. And we're going to be done with this one very quickly. So it's negative 3 minus 3y equals negative 15. I add 3 to both sides, and I get negative 3y equals negative 12. And I get y equals 4. I already know what x equals, so I do not have to plug this back in. If I did, I would get x equal to negative 3 again. And so my answer is negative 3, 4. On to number 5, the top equation is already solved for, which has a slope of 2/1 and a y-intercept of 4, which I'll go ahead and graph. And I'll solve this next one, and that'll get me y equals 2x minus 4, which means it has a slope of 2 or 2/1, a y-intercept of negative 4. And you may have already noticed, since they have the same slopes and different y-intercepts, that they are in fact parallel, which means that there is no solution. Oop, try that again. I graphed my purple one poorly, because this purple one is supposed to be a negative 4 for the y-intercept. Silly me. And so let me fix my purple one by now graphing it correctly, which means it's just the exact same line as this. And so instead of being no solution in parallel lines, they're the same line, which means there's infinitely many solutions. They share every single point. So on this, we already have a variable solved for, so we take all this, plug it in for y, and we get 6x minus 3 times 2x minus 4 equals 12. Distribute my negative 3, and I get 6x minus 6x plus 12 equals 12. 6x minus itself is no x's, or 0, so I have 12 equals 12. That's no variables, a true statement, so it is infinitely many solutions. They're the same line, just like we saw on example 5. Moving on to example 6. This top equation is, when you put it in slope-intercept form, y equals negative 2x minus 8. The bottom equation is, when you put it in slope-intercept form, y equals 3/5 x plus 5. So this top equation has a slope of negative 2 over 1 and a y-intercept of negative 8. And the bottom equation has a slope of 3 over 5 and a y-intercept of 5. And so those intersect at this green point, which is negative 5, 2. Over here for substitution, we want to get this y solved for. To solve for y, we already know that it would be y equals negative 2x minus 8 like we saw on graphing. I now plug this in to the other equation for y. I get 3x minus 5 times negative 2x minus 8 equals negative 25. Distribute my negative 5, and I get 3x plus 10x plus 40 equals negative 25. Combine like terms and I get 13x plus, I put equals, plus 40 equals negative 25. Then I will go ahead and subtract 40 from both sides. And I get 13x equals negative 65. And if I divide by 13, I get x to equal negative 5. Plug it back into any of the equations. I'll choose my one that I revised or changed up here. And I get y equals negative 2 times negative 5 minus 8. And I get y equals 10 minus 8, which is y equals 2, which is the answer we got of negative 5, 2 when we graphed it as well. Number 7, this top equation is y equals negative 2 over 9x plus 3. The bottom equation is y equals 1/3 x plus 8. Graphing this top equation with a slope of negative 2 over 9 and a y-intercept of 3. And graphing this bottom one with a y-intercept of 1/3 and a y-intercept of 8. I realized a mistake I made. On my purple graph, I did a positive 2 over 9 slope instead of a negative 2 over 9 slope. I was looking at these and realizing they weren't going to intersect, and I knew they were supposed to intersect on this problem because I had already had the key made. This will work much better. Some of you may have had this already and been like, wait, Mr. Kostel, what are you doing? And so I apologize for that. It seems I made another error. Oh, silly me. I know I have a y-intercept of 8, but I started at 9 on my green one. Double mistake here. So let me erase my points that I have for the green and fix that. Mistake city over here, I suppose. That works better. And so now my answer is right here, which is negative 9, 5. That'll be the answer we get for substitution in just a moment. Once I solve for x in this equation. Solving for x in this equation is x equals 3y minus 24. I plug this into the top equation for x, and I get 2 times 3y minus 24 plus 9y equals 27. So I distribute the 2, And I get 6y minus 48 plus 9y equals 27. Combining like terms, I get 15y minus 48 equals 27. And if I add 48 to both sides, I get 15y equal to 75. And dividing by 15, I establish my y is equaling -9. What did I do? Oh, it's going to be 5. Why did I say -9? That's going to be my x value later, as we know. And now I plug this in. I'll plug it into my newest equation that I did. X equals 3 times 5 minus 24. 3 times 5 is 15. And 15 minus 24 is -9. And I get 5 comma -9 again. I said 5 comma -9. That was backwards. X comma y, -9 comma 5. I believe that was 3 different mistakes I made on that problem. Man, being human is hard. Number 8, I solve this top equation for y and I get y to equal 1/2 x minus 4. I solve the bottom equation for y and I end up getting y equals -4/3 x plus 7. The top equation has a slope of 1/2 and a y-intercept of -4. The bottom equation has a slope of -4/3 and a y-intercept of 7. Did I make a mistake here? Let me look. I know I'm prone to that, apparently. I'm counting out what I did here, knowing I must have done something wrong. Oh, I see what it is. On my purple one, it's 1/2 for my slope, and I did 1/4. Oh, darn it. I best be fixing that. Another case of the humans. Now we get these actually intersecting at a point. And so my ordered pair here is 6 comma -1. As I solve this one by substitution, I'm going to solve the top equation for x because it has a coefficient of 1. That results in x equals 2y plus 8. I'm going to plug that in for x, and I get 8 times 2y plus 8 plus 6y equals 42. Distribute the 8, and I get 16y plus 64 plus 6y equals 42. Combining like terms here, I end up getting 22y plus 64 equals 42. Subtracting 64 from both sides, I get 22y equals -18. Sorry, try that again, -22. At least I caught that mistake quickly. And divide by 22, and I get y to equal -1. Now I plug that into either my original equations or my revised one, which is what I'll do. And I get x equals 2 times -1 plus 8, which is -2 plus 8, which is 6. So that's 6 comma -1. On to number 9. So I solve this top equation for y, and I get y to equal x minus 7. I solve the bottom equation for y as well, and I get y to equal x minus 2. Top equation has a slope of 1/1 and a y-intercept of -7. Bottom equation has a slope of 1 over 1 again, and a y-intercept of -2. And since they have the same slope but different y-intercepts, these are in fact parallel, and thus have no solution. Which is what we'll see on the substitution portion of this problem. It's wigging out over there. And so now over here, as I start solving this, I will pick this one because it has a positive 1x as a coefficient, and solving that I get x equals y plus 2. If I plug this in, oops, I hit the wrong button there. It's in my other equation for x. I get 2 times y plus 2 minus 2y equals 14. So I distribute this, and I get 2y plus 4 minus 2y equals 14. That gives me 0y, so I just have 4 equals 14. And that is inaccurate, it's false. So this is also no solution. As I do number 10, I solve this top equation for y, and I get y equals to 1/4 x, or 1/4 x plus 0 technically. I solve the bottom equation, and I get y equals -1/2 x plus 6. So this top equation has a slope of 1/4, a y-intercept of 0. It is not wanting me to connect my line. Oh, eventually it went. Now as I graph my second one, slope of -1/2, my y-intercept of 6. And that is the ordered pair, 8, 2. And so here, doesn't really matter which one I solve for. Actually, I already have one solved for, silly me. So I'll take all of this, plug it in for x. I'll get 4y plus 2y equals 12, giving me 6y equals 12. Divide by 6. And y is 2, like we found already on our graphing. Plug this into either equation. I'll pick the top one since it's already solved for x, and I get x equals 4 times 2. And last I checked, 4 times 2 is 8, and thankfully I didn't make a mistake that time. And I get 8, 2. And that wraps up Section 2, Solving Systems by Substitution.